Good morning and good afternoon from the Center for Space Resources at Colorado School of Mines. My name is Gordon, and today I'll be talking about laboratory investigations into space mining, and more specifically about water extraction processes in an extraterrestrial environment. And since we have a limited time, I'll just jump straight into that. So last year at your first conference, I've been providing some of the overarching insights into the subject of water resources in space, about the locations, potential, and concepts of utilization. Now I'll show you the methods of how we can investigate those problems in lab conditions for a very specific environment where we can find those resources, which are permanently shadowed regions on the moon. So permanently shadowed regions, for those of you who don't know that, or PSRs, are those craters on the moon poles where sunlight never reaches. And this state of being lasts for billions of years, thus creating a very stable cold traps, which can provide a stable but extremely cold place for volatiles to deposit. Even in such extremely high vacuum mass on the moon. Those volatiles include hydrogen sulfide, carbon dioxide, and many other nasty compounds. But what's most important is water, with an average content of around 5% at Cabezo's crater. And it's really great because we can build commercial and science cases for a moon base within vicinities of those regions, like here shown on the floor of the Amundsen crater. Or we could utilize near-continuous illumination around PSRs to mirror energy for our utilization needs. Something as simple as water creates a plethora of ways to provide various end products for the customers on the moon and within the cislunar sphere. From potable water through oxygen and hydrogen gases, energy storage, to finally rocket-grade propellant, for profits and for sustainable development of human presence in space. But before we send anything to space to test our methods and technologies, before we actually start utilizing those vast resources, we need to focus on testing those processes in a lab environment. Because guess what? We know almost nothing about them. So my job here is to simulate the environment of extremely cold temperatures and extremely low pressures, and simulate our interactions with icy lunar regolith that we might possibly find within PSRs, as faithfully, as feasibly as possible. In other words, that includes the use of vacuum and cryotechnologies, sadly in an Earth gravity environment. Thanks to courtesy of mine, I'm using this 2-feet vacuum chamber, which is the basis of an in situ experimental probe. This is the instrument in the middle of the picture. The chamber is equipped with a cold trap and this big flange to the right, 2 pressure gauges, and of course uses a vacuum pump to suck the air out of it when the pieces are connected and the experiment is running. The second important part is a cryobed, which is used to contain a sample of icy regolith and to cool it down around minus 180 C. The cryobed is a big chunk of metal, which is bathed in liquid nitrogen, but also filled with liquid nitrogen through 2 inlets. It is a cool down method developed here at Mainz and proved to be the most efficient of all of them. Apart from that, the sample gets manually inserted heater and thermocouples to heat up the sample from the sensor and measure heat transfer and thermal properties of the regolith. Lastly, there's a LabVIEW program that logs all the data and provides the control for the experiment, most importantly for the heating. So, how it's all done? I will guide you through all the steps in detail. At first, you need to create a sample. We make it by mixing a JSC1A regolith, which is a mare regolith of the moon, with liquid water in specific proportions. It is not, however, the best method to do that because ice in space is implanted in the regolith through vapor deposition process, which creates an ice-cemented regolith through a net of ice dendrites. This is unfortunately a difficult task, requiring specific instruments and days or even weeks to complete just one faithful sample. That's why we're not using it right now. Mixed regolith and water are then placed within jars where water soaks through, then within sample holders, compacted using surcharge, as here in the picture, and placed within a freezer for better cohesion and faster cooling. Next step is to cool down the sample using the cryobed. Sample holder is covered and placed in a liquid nitrogen bath, where it cools down to a lovely minus 180 C. After about an hour, holes are drilled for heater and thermocouples, and the bed is placed in the chamber where everything else is connected and the chamber is closed. That is where we start the experiment. There's a specific pump down procedure I came up with, which uses multiple pump downs over the course of the run. When the pressure starts to plateau for the first time, heater is turned on and set for 200 C. And that's where you can sit back, relax, and drink a couple of teas and coffees, because we have around 6 hours of entertaining graphs to watch. And unironically, it's pretty entertaining to me. After the temperature reaches minus 42 C, we can prepare to finish the run. Repressurize the chamber, take some photos, and then take out the cryobed, take more photos, measure sample weight, make cross sects, make smaller batches, put everything in the oven, and forget about it. But this wasn't the procedure I've been following from the very beginning. I had to come up with it through a series of trials and errors, like here in this video. Hopefully you can see that. I'll show you again. Can you see the video? Yes. It's a nasty process and messy. Thank God our vacuum chambers allow for dirty experiments. But sometimes it can be seriously dirty, and that's no good, because if that's how the process occurs in space, we have a major technological problem. Another thing is that icy regolith is literally hard as rock, with just as little of 5% water. It is almost impossible to drill through, and you have to really push yourself for a couple of minutes, because I drill holes manually. And sometimes things get stuck, like here when I've been trying to take the core out. Another thing is that everything before and after run is a fast-paced thing, which may result in mistakes. And you can imagine that mistakes when working with cryoliquids may be quite bad, so safety first. So, what I've learned so far. The process is working, but it's so slow. It takes more than 6 hours to heat up the regolith from minus 180 C to minus 40, and around a day to heat it up to 0 C. And we're talking here about a radius of only 2 to 4 centimeters, with conductive heating by a cartridge and radiated heating from the chamber environment. It's also behaving strangely on the process diagram, which is the pressure temperature diagram, like here on the example. There are pressure spikes, pressure drops, and interestingly, no significant mass change of the sample itself. So why is that? Well, one of the possible explanations is that water is moving within the sample rather than out of the sample. So first you have a more or less uniform thermal properties. Then part of the sample starts getting desiccated up to finally becoming dry. So what we're dealing here is thermal properties, anisotropy that is created during the process of heating. The amount of data that I've gathered so far, and would gather some more over the next 1.5 months of my stay here at Mainz, would allow me to determine the thermal properties of ICJ-Symulowanie model heat and mass transfer during the process of water extraction, create a simulation of those experiments in the off-the-shelf FAM programs based on experimental data, and provide a data processing methodology that I'll use further in research of the same problem but in Martian environment. As always, I'll conclude with an inspirational quote, this time from David Scott, astronaut of Gemini 8, Apollo 9, and Apollo 15. As I stand out here in the wonders of the unknown at Hadley, I sort of realize there's a fundamental truth to our nature. Man must explore, and this is exploration at its greatest. I tell you, as NASA is going back to the moon in unmanned missions, as Europe is going to the moon with ISOU mission, that we at the Space Research Center are proudly part of, we were born just the right time to explore the moon, Mars, and beyond. Thank you so much for your attention. I wish you a great afternoon, fantastic event, and Godspeed to you all.